So, have you ever wondered how a machine can actually diagnose a rare disease? Or how a computer program can look at a patient's lab results and predict, with shocking accuracy, exactly how many days they'll need to stay in the hospital? Well, welcome to today's Explainer. I am so incredibly excited about this one, because we're taking a journey into the heart of a life-saving algorithm used all over modern medicine. It's called K-nearest neighbors, or just KNN for short.
To really kick things off, let's frame this whole explainer around one fascinating question. How on earth does a computer diagnose a patient without using a rigid mathematical formula? It sounds kind of impossible, right? Machines run on math. But the secret is that these systems can actually learn almost exactly like human doctors do, by relying on past experiences and looking for patterns. Let's see how this all breaks down.
All right, here's our roadmap for today. We're going to cover the ward round analogy, choosing the k-value, calculating medical distance, a step-by-step case study, lazy learners and trade-offs, and finally, the real-world stakes. Let's dive right in.
Section 1. The ward round analogy.
I always like to start with the why, and honestly, the best way to understand this algorithm is to picture a totally normal human scenario. Imagine a doctor seeing a 58-year-old patient with chest pain. That doctor doesn't sit down and solve a complex algebra equation to figure out what's wrong, do they? No. Instead, they search their memory. They ask themselves, okay, which past patients have I treated who looked just like this one? That intuitive thought process? That is exactly what KNN does. Now let's clear up some of the technical jargon you might hear. KNN is a type of supervised learning. That just means the algorithm learns by example. It uses a giant library of past, confirmed cases, like looking at an answer key. It's also called non-parametric, which is honestly just a really fancy way of saying it doesn't try to force one single mathematical equation onto every single patient. It classifies a new case purely by its similarity to those known past cases.
And this is absolutely brilliant, because it perfectly illustrates the difference between KNN and the standard math you probably learned in high school. You know how a traditional model like linear regression tries to draw one massive straight line through all the data to find a global trend? Well, KNN doesn't care about the global trend. It's all about local influence. It looks at a massive database of, say, 100,000 past patient records, and it just wants to find the 5 or so people who look exactly like the person sitting in front of you. Basically, your closest matches decide your fate.
Which brings us to Section 2, choosing the k-value.
You're probably wondering, okay, so what exactly is K? Simply put, K is your virtual second opinion panel. It's the precise number of past patients the algorithm is actually allowed to look at to make its decision. And changing this single number changes absolutely everything. Think about the trade-off here. Imagine setting K to 1. That's like asking only a single doctor for their opinion. It's super fast, sure, but it is hypersensitive to noise. What if that one past patient was misdiagnosed? You get massive variance. On the flip side, what if we set K to 50? That's like polling 50 different doctors. It beautifully smooths out any weird noise, but if you have a rare disease, your few matching cases are just going to get completely outvoted by the healthy majority. So, how do we find the right balance?
Well, how do data scientists actually pick this number in a real functioning clinic? You never ever just guess by eye. You test different numbers mathematically through a rigorous process called cross-validation. Also, here is a really brilliant pro tip from our source material. Always use an odd number for K if you're deciding between two outcomes, like disease or no disease. That way, you literally never end up with a 50-50 tied vote. A very common starting point is simply taking the square root of the total number of patients in your database.
Let's move on to Section 3, calculating medical distance.
We keep saying the computer finds the closest matches, but how? Computers don't have eyes? To a machine, patients are just lists of numbers. Well, the secret is plotting these medical stats physically on a graph. Imagine you're looking at a graph right now. The horizontal line at the bottom, the x-axis, is a patient's age. The vertical line going up, the y-axis, is their blood pressure. Every past patient is a dot plotted exactly based on those two numbers. Now, plop our new unknown patient right in the middle of that graph. By visualizing them like this, the math of finding the closest matching patients becomes as incredibly simple as literally measuring the space between dots on a piece of paper. And to measure that space, the algorithm uses something called Euclidean distance. Now, I know the formula for this might look a bit intimidating, but I promise you, it is quite literally just measuring the physical straight-line gap between 2 points on the graph we just imagined. Think of it like taking a ruler, slapping it down on the paper, and drawing a straight line from one dot to another. That line is your distance. The shorter the line, the more medically similar the patients are. It's really that simple. But wait,
I have to highlight a massive trap here that our source material warns us about. Distance is completely meaningless if we don't scale the features first. What does that actually mean? Well, think about it. A blood glucose level might be a huge number, like 150, but a body mass index might be a really small number, like 25. If we don't mathematically shrink these numbers down so they are on the exact same scale, the massive glucose numbers will completely overpower and drown out the smaller BMI numbers when the computer calculates the distance. It totally skews the results.
Okay, let's cement all this foundational knowledge with Section 4, a step-by-step case study.
Let's pretend for a minute that we are the algorithm, okay? We've been tasked with predicting a patient's length of stay, meaning exactly how many days they'll be stuck in the hospital for pneumonia. To do this, we always follow a simple two-step process. Step 1, calculate the distance to find the K nearest patients. Step 2, make the decision. Now, if we were diagnosing a condition like cancer, we'd use something called classification and just take a majority vote. But because we're predicting a continuous number, days in a hospital bed, we use regression. That simply means we take the exact average of our nearest neighbors.
So here is our raw data. We've got 5 past patients. We know their age, their CRP level, which is just a common inflammation marker in the blood, and their exact length of stay in days. Suddenly, a new patient walks through the hospital doors. They're 62 years old with a CRP of 95. Remember, you're the algorithm. Your job is to figure out which of those past patients is mathematically closest to our new 62-year-old. Let's set our K-value to 3.
All right, after crunching that straight-line ruler math, here are the results. The closest match is patient C at a distance of 5.83. Next up is patient B at 26.2 and patient D at 27.7. So C, B, and D are our 3 nearest neighbors. But hey, notice the warning here. Our source points out that because the raw CRP numbers were so much larger than the age numbers, the unscaled CRP data completely dominated this calculation. In a real functioning hospital pipeline, we absolutely would have scaled these numbers first to make it perfectly fair.
And here is the visual proof of our math. See how our new patient is right in the middle and they mathematically cluster right together with those 3 closest matches? The algorithm completely ignored the other patients because they were just too far away on the graph to be relevant to this specific diagnosis.
So, what's the final punchline? We take the known hospital stays of our 3 nearest neighbors. One stayed 7 days, one stayed 9 days, and one stayed 5 days. We add those up, divide by 3 to get our regression average, and boom, the computer successfully predicts a 7-day stay for our new patient. It's incredibly elegant when you break it down like that, isn't it?
Now let's pivot slightly for Section 5, lazy learners and trade-offs.
I want to introduce you to a really fun and kind of counterintuitive piece of machine learning jargon that directly impacts how this runs in a busy clinic. KNN is officially classified as a lazy learner. Literally, that's the term. It means the algorithm actually never learns a real underlying rule or formula. It doesn't study the data to uncover some hidden truth about human biology. Instead, it just simply memorizes the entire patient registry to reference later. Think of it like a student who memorizes an entire textbook without actually understanding a single concept, just so they can look up the exact answers during an open book test.
Naturally, this laziness creates some intense trade-offs. The pros? Well, doctors love it because it's completely transparent and auditable. If the algorithm suggests cancer, you can point to the exact 3 past patients it used to make that call. No black boxes here. But the cons? Because it has 0 initial training time, the algorithm is notoriously slow right at the bedside. Every single time a new patient arrives, it has to scan through every single record in the database all over again. It also really struggles with massive data sets, like genomics, where there are tens of thousands of features to measure.
Finally, let's bring this explainer home with Section 6, the real-world stakes.
We've talked extensively about math and graphs today, but in modern medicine, this algorithm is used for the highest stakes imaginable, like diagnosing breast cancer based on tumor shapes. And when we're diagnosing cancer, we have to talk about the very real cost of being wrong. Look at this data. The algorithm was incredibly accurate, 95.6% overall accuracy, but notice the top row. At the default threshold, the algorithm completely missed 4 actual cancers. Is 95.6% accuracy actually good enough if 4 people are sent home thinking they're entirely fine? Now, if we adjust the algorithm's sensitivity down, as you see on the bottom row, we miss fewer cancers, only 2 instead of 4. But the unavoidable trade-off is that we generate 4 false alarms, which obviously scares perfectly healthy patients. And this brilliantly illustrates our final takeaway, which is perfectly summarized by this quote from our source material. Lowering the threshold buys 2 fewer missed cancers for 3 extra false alarms, a trade the oncologist, not the algorithm, must make. At the end of the day,
K-nearest neighbors is an incredibly powerful tool that effectively mimics human intuition. The math can quickly find the patterns, but the complex, ethical decisions of how to actually use those patterns to save lives, that remains firmly in the hands of human beings. It really makes you wonder, as algorithms become even more advanced, how much of our medical fate are we truly willing to hand over to a machine? Something to think about.